in our last lecture, we said that let's try to consider this system where we have system 1 and system 2 basically initially isolated from each other. So the phase space should be considered as the product of phase space of system 1 with initial energy E1 initial times the phase space 2 with initial energy E2 initial. Okay, that's the initial configuration. And we also require that the energy to be conserved. That is, at some point we will remove this isolated wall by some conductive wall. So we require, but we still keep the composite system to be an isolated system. So we require the energy to be conserved. Okay. So now, now we change our wall to be a thermally conductive wall, which means that now system 1 and system 2 can exchange their energy. Okay. So when they are able to exchange their energy, what that means is that before we use this conductive wall, the energy should be independently conserved. That is, we have two constraints. These are constraints. Now, because they can exchange energy with each other, so in this setting, we basically relax this constraint into a more flexible constraint. That's basically the total energy should be conserved. Okay. So because it is relaxed, so the phase space volume should be considered as the summation of all the possible energy of our subsystem 1. We should include them all. So it means that for a specific energy E1, the phase space should be the product of these two systems. But with another different energy E1, we will have another product, so we need to add them up together. Okay, and the reason we will need to consider that is because now the constraint is more flexible, and because of that, the accessible phase space volume is increased. It also suggests that the entropy should grow. Okay. But we should ask a question: at equilibrium, what happened? What happened is that the energy for the system 1 will reach the E1 equilibrium value, and the energy for the system 2 will also reach the E2 equilibrium value, but the total energy should be E total. Okay. So the first thing, as I discussed in the last lecture, is that if we try to evaluate the equilibrium phase space volume at the equilibrium energy configuration, we end up with this expression times and at this point it seems like it is obviously smaller than the total accessible phase space volume that we just described here, because this expression includes all the possible energy configuration of the system 1. So that's one question for this expression. So should we really consider it faithfully like that? And another question is related to the fact that now we are saying that we want to sum over all the possible energy. But that also suggests that if we start from some, let's just keep track of the system 1, okay? If we start from some energy 1 of our initial configuration, then it might decay into our system one's energy 1. Maybe I should use another label. Let me call it A, EA of 1, which is the one of the possible energy of our system. But once it decay into that channel, it could decay into maybe further. Oops, not B, still A. But to another energy, EA2. Okay. And so on, it can do. But there's another possibility is that you choose another decay path that the energy can go from E1 initial to EB1, and then it goes to EB2. Okay, and go on. So when we take this summation, the first challenge we need to face is that, does that mean like this phase space volume actually will depends on how the system decay into the equilibrium configuration, or how the path of the energy that it choose. So it seems like the definition of this gamma will actually depends on the path of energy, which is something that we don't want it to have. So, so the question that we want to ask at this point is that, even though we formally write down what are the possible volume of the phase space gamma, but how it is related to the equilibrium configuration of our phase space. Okay, so that's the question that we are trying to ask. So, so let's try to build this connection by doing the following things. So let me just rewrite what we already had above about how we calculate the total accessible volume of the phase space. Basically, we need to sum over all the possible configurations of the allowed energy of our system 1. Okay. Oops. Sorry. Okay. So this is just a rewrite everything. I didn't do anything new. So here we want to use the Boltzmann's postulate to some extent approximate what is the value of this phase space. So I can do that because if I follow this expression strictly, I can replace this phase space volume by some exponential of the entropy expression. So it ends up to be things like this. Okay. So once we have this expression, as we have done several times, discrete summation usually is really difficult to deal with. So one trick is that you said that maybe the energy level is very dense for a many-body system. So you can approximate this discrete summation by the integral, but with some kind of energy difference. Then you can do the continuum version of this summation. And also, because now you are working in a continuous version of this summation, you can actually expand this entropy around its equilibrium volume. Equilibrium value, sorry. So, so let me just write down what that means. So here is like once we evaluate or like expand this entropy expression nearby its equilibrium value, that's the leading order. And because at the equilibrium, we know the first derivative of that should be 0. Okay. So so what we are going to have is the quadratic correction. And here we also implicitly use the energy conserving condition. Okay. Of course, there are stuff, but I'll just leave the stuff because they are high order corrections. Okay. Wait, I think I made a mistake. Sorry, I think I'm a bit confused. Let's see. Oh, I think I'm fine. Okay, so the first thing that I think we have used that several times. The first thing is that we know entropy is a concave function. So second derivative with any extensive variables should be smaller than 0. That's one thing. And the second thing is that as we know, this thing is intensive, and x is some extensive variable. So this thing will be of 1 over n when we take the thermodynamic limit. Okay. So so if we want to evaluate this expression that we just derived by expanding it around the equilibrium value, then we'll see this gamma is approximately exponential some equilibrium entropy divided by kb times something, and this something came from the integration of the E1, but now we see it is some kind of Gaussian integral, so we know what's the result of Gaussian integral. Basically, it will just give you some square root of pi divided by the coefficient here, which is 1 over n. And if I divide it by 1 over n, it will just give me pi times n. Okay. And also we know that entropy itself is an extensive variable, which means that if I just look at the n dependence, this thing is basically exponential something with the n here times the square root of n. Okay. So what does that mean? It means that this contribution is actually not super important because there's a super dominant one, which is exponentially large in your system size. So so what can we say about that? Is this is basically related to the equilibrium phase space volume. So from this expression, we can see that the accessible phase space volume, if we consider all the energy, and the phase space volume that we only consider the equilibrium configuration, they are different with each other. Or maybe I can say the phase space volume with all the energy is larger than the equilibrium one, but it is not much larger. It is just larger with the power of square root of n. So to some extent, the leading order contribution is still this exponentially large n factor. So when you calculate the entropy, basically you take a natural log of the gamma, then you'll see the dominant contribution is still from the equilibrium entropy and plus some log n correction that you don't care about. Okay. So so it is a very interesting observation because it tells us that if you try to draw some kind of plot about what is the phase space that is accessible at a certain energy E. So let me just use E1 as our parameter to understand what is the behavior of this phase space size. You'll see that actually it is quite dominated by the configuration nearby the equilibrium volume. Okay. So if you include all the rest other than this equilibrium volume, it will basically just give you some square root of n contribution. So so here we have the following relation. And again, the relative error of the energy will go like 1 over square root of n, and it will go to 0 as n goes to infinite. So this is very similar to the central limit theorem type of analysis that we have done in the previous examples. But also it tells us something, that this fluctuation of n is basically of statistical nature. Okay, but in the lab or in the experiments, you always have a finite resolution. So so this expression also tells us that the resolution of energy, let's say it is delta E, is not important as long as this delta E is much smaller, or at least it is smaller than delta E for the most of time, because this thing will goes like square root of n. Okay, so when the particle number is huge, you actually do not really care about the individual resolution of your energy. Okay, so now I'm going to almost like end the story about the phase space and then go to the example. So one of the questions that I haven't addressed is that now we are talking about something like classical mechanics. How about the quantum one? Okay, so in the classical one, the definition of entropy, or the postulate that given by Boltzmann, is by this phase space volume. But in fact, this phase space volume actually depends on how you define the unit of your volume. Okay, because at the classical level, actually there's no lower bound of the product of x and p. But in the quantum level, we have a uncertainty principle. That's basically, this thing is of order h, where h is the Boltzmann constant. And this gives us the nature unit of the phase space volume. And it turns out that when we try to generalize it to the quantum version of Boltzmann's postulate, you can simply consider it as nature log of n, where n is the number of eigenstates in the region with specific extensive variables. Okay, so that's like you just count the state. If you give me a specific energy and tell me what is the energy of the size of the energy shell, then we just count how many states within this energy cell. Okay. So there will be a very simple exercise of the homework that is basically ask you to show why or how to derive that in a quantum system there's a very natural phase space unit, such that you can use it to count how many states in your system. Okay, so I think that's basically the case, and I'm going to talk about one example very quickly. That's basically the ideal gas model again. And we'll try to evaluate what is the phase space volume of the ideal gas system. And from there, we can derive what is the entropy for ideal gas system. And once we know the entropy of the ideal gas system as a function of some extensive variables, then we can derive the state equation of the ideal gas. So that's like the basic logic of what I'm going to do. So for ideal gas, the Hamiltonian is relatively simple. We just have m particles, and we just sum up all the kinetic energy of our system. And our system is basically confined in a potential that's specified by this U of Ri. And U of Ri, I can write down a more mathematical description, but I think drawing the figure is already enough. It just says that if you get outside of the size of your box, basically the potential energy cost is infinite. So the particles do not want to do that, and they are all confined within a certain area within this box. Okay, so now we can ask how to derive the accessible phase space for this system. And so here is one suspicious term, 1 over m factorial. It is related to the indistinguishability of the of the particles. So to some extent, it already contains some quantumness inside. Okay, even for ideal gas situation. And it turns out that this 1 over m factorial is important in order to keep the entropy to be an extensive quantity. But I'm not going to specify too much about that. So let me just continue. And as I mentioned, that in principle, in a classical system, you don't really need to worry about this H. But as the quantum system or already specify a natural unit for our phase space volume, so why not just keep it there? And now we are trying to calculate what is the corresponding phase space of our system. So we'll make an integral ranging from the first particle to the nth particle, and we want to integrate over the coordinates Ri and the momentum Pi. And here we want to define what is the accessible phase space of our system. So for the coordinates, it's relatively easy because we already defined what is the volume of our box. But for the momentum, in the last time, we didn't really specify how it is done. But here, I'm going to write down explicitly how we define the accessible region. So this is the total kinetic energy, and we require it to have the total energy to be specific energy E. Okay, so this is basically the idea of how to calculate the phase space volume. So the only purpose for this delta function is that it specifies the integral such that we only take those integral with the corresponding total energy E. Okay, so now we should be able to do the integral. As I mentioned, that this integration over space is trivial. It will just give you volume for each particle. Since we have m particles, so we'll have a factor v to the power of n. And the m factorial is there, and h to the 3m factor is still there. So the only non-trivial integral that is left is this momentum integral. Okay, and from the property of delta function, we can take out the factor of 1 over 2m. Okay, and this integral should be something that you will be able to work out in your homework too. And eventually, you will get this expression. And this is the gamma function. Okay. So that's the important moment that we evaluate the phase space volume for the ideal gas system. So how to evaluate the entropy of that? It's also simple. We just times Kb with the nature log of the phase space volume. Okay. And using the Stirling's approximation, we can simplify these factors with n in the exponents, and eventually you will get this following expression if you do it carefully. And here this E is just the Euler number. Let me write it. Euler number. 2 point something. Okay. And you can see explicitly that it is an extensive quantity because it's proportional with the system size n. And you can ask, what if 1 over n factorial is not there? Eventually you'll see you cannot get an extensive one. Okay. So once you got the entropy, the rest of the stuff is easy because you can calculate the temperature by taking derivative with the entropy with respect to your energy, and you'll see it looks like that. And you can also calculate the pressure. Just Vn. And you will get the ideal gas equation. Okay, I'll stop here and we'll take a 20 minutes break, and then we'll continue the rest of the today's lecture by really entering the idea of ensembles. Okay, so see you in the next lecture. Hi everyone, we will continue our lecture. So before the lecture, I want to emphasize something, that the first thing is that the TA section is really help you to understand what is going on in the homework. And it will be very important for the midterm exam because, you know, midterm exam is an exam that will give you some problem, and those problems usually are very correlated with the homework, okay? So if you have any problem about the homework, that usually means that there will be some problem in the midterm that you might feel not really, you know, understood. So try to go to the TA section if possible. And if you are not able to go to the TA section, but you still have some problem about your homework, please email to me or email to the TA and ask for discussion time. Because if you don't ask, we will not know what is bothering you. We are not going to know which part I should emphasize more and things like that. So please try to do that. And also, some of the important mathematical or proofs, I will put it in the homework section such that you can go through the derivation by yourself. The purpose is that to make sure some of the fundamental you need to be familiar with, okay? For example, the Gaussian integral is extremely important. So if you don't know how to do it, please follow the homework, I think, or follow the lecture note. I think I have a lecture note saying how to do the Gaussian integral. If you don't know how to do that, please go to the online lecture, okay? Or try to ask the TA or me. And also, another thing is that I think if you feel like doing the homework is kind of stressful, please don't feel panic. Just go to the TA section. They are very friendly and they are willing to help you, okay? Even though they are not going to help you directly to write down your homework, but they will try to clarify some questions and try to guide you to the right direction, because they all have the solution of the homework, so they should be able to understand that and explain to you. Okay, so that's it, and we'll continue our derivation. And one of the step I skipped through is this delta function in the previous derivation. That there's a property about the delta function. If you try to take out the coefficient a outside of the delta function, you cannot just pull it out. It actually becomes the inverse, like a inverse, when you do the change of variable. And if you want to prove that, easy way to do that is you just do the integration on the left hand side or right hand side, and you are able to convince yourself that's the property of delta function. Okay. And I think that's one thing. And another thing is that when I discuss about the this volume integral, I kind of say things very fast. So here's the factor h to the 3n. So where does it come from? It came from the fact that we try to argue that in the quantum mechanical system, there's a some kind of nature unit for our phase space volume. So the point is that if you have x and you have one conjugate momentum with your space coordinate p, then each x and each p will contribute a factor of h. So when you are doing this integral, you will have 3n pairs of Ri and Pi. Sorry, maybe I'll just write it explicitly, Ri alpha and Pi alpha. And here I goes from 1 to n, and alpha is just x, y, z. Okay? Because of that, each pair of them will give you a h. So because we have 3n pairs of them, so we have a factor of h to the power of 3n. So why it is so? Why we consider h as a nature unit of our phase space volume? I'll ask a question in the homework section that you should be able to prove that by studying the distance, or like the volume covered by one quantum state in some simple examples, including the simple harmonic oscillators or free particles. So both of them will give you the answer why this fundamental unit of phase space volume should be of order h. Okay, so that's basically the idea. And okay, so let's continue. So once we got the expression for our phase space volume, then we are able to derive the expression for entropy. And as I mentioned, you can just take derivatives with respect to energy and volume, and you got the expression that we are very familiar with for the ideal gas case. The second equation is just PV equals to NKBT, which is the ideal gas equation. And the first equation actually tells us that the energy should be equal to, or the internal energy should be equal to 3/2 of NKBT, which is the the ideal gas internal energy that we are familiar with. So at this point, you might have a question that, okay, so we start from statistical mechanics and we got something related to thermodynamics. So why bother to learn statistical mechanics once I know how to use thermodynamics and everything is there? So the key question is, actually there are some additional information that statistical mechanics can provide us. So one of the very powerful stuff that statistical mechanics provide is that it can provide the probability distribution, or the probability for some microscopic configuration. Okay, and once you know what is the probability of the microscopic configuration, then you can ask, what is the expectation value for certain observable? Usually it's denoted by these angle brackets. And it is quite easy to calculate, because what you can do is that you calculate this observable as a function of your microscopic degrees of freedom. and then you times it or you weight it with the probability of this microscopic configuration. So if you got the probability distribution for microscopic configuration, then you're able to do this kind of calculation, which can give you some quantity that is beyond the standard quantity of thermodynamics. So that will be useful. Okay. So in the following, we are going to discuss like how it is possible. Let me put it in this way: how is it possible that we are able to find this probability description for the microscopic configurations? So we'll start from something that's called somehow my pen is kind of, I don't know, maybe it is out of juice or something. That's something called the microcanonical ensemble. Okay. So there are several ways to introduce the microcanonical ensemble, and some of the textbook will take the following route, which is very easy. You can just say that in this system, the system that we are considering is the system that the energy E, or the internal energy, is a conserved quantity, or this energy E is fixed. Okay. And every microscopic state in the phase space that is constrained by this conserved energy E has equal weight. Okay, and if it is the case, then the expectation value of A should be easy, because every point in your phase space gamma E is weighted equally, so the normalization constant is naturally 1 over gamma E. Sorry. And then you weight every configuration equally, so every A with different microscopic configuration can C will be counted once exactly. Then that is the expectation value for the equilibrium value of observable A in micro ensemble. Okay, so that's like some kind of defined way. If you want to explain the ensemble theory according to a definition, sometimes people will take that. So we'll try to ask another question, like, even though it is usually accepted like that, but why it is reasonable? Why it is reasonable to make this assumption? Okay. By the way, here A is an extensive variable. Okay. So we'll try to ask this question and see whether we can build some intuition from the postulate of Boltzmann's entropy formula. So as we know, if we have some entropy that is specified by some extensive variables, so let me just use X to represent the set of all the extensive variables other than A. And here this A is the some value of the extensive variables that is not the same as the equilibrium value. Okay. So we know that if it is in equilibrium, this relation should hold, because the equilibrium configuration should have the maximized entropy. Okay. And then we can try to be a bit more specific. What is the expression if we try to write it down using the Boltzmann's postulate? So basically, we just include all the microscopic configuration in the phase space gamma, and we evaluate or we restrict the phase space to have observable A to be the value A that is assigned, that is different with the equilibrium value A star. Okay, so that's the entropy, and at the equilibrium, A will be the equilibrium value A star, and you should be natural log of the phase space of A star. Okay, so in the previous discussion, we kind of suggest that when we discussed the behavior of energy, we said that, even though we want to consider all the accessible phase space volume, and it turns out that most of the contribution came from the equilibrium volume. So we want to ask, can we make similar argument in this case? Okay, so one way to do that is that we can ask, what is the volume if we give the observable A to have the value this little a, comparing with the phase space volume, that is A is at the value of the equilibrium value. Okay, we can try to evaluate this thing, and let me try to express that a bit more formally, but maybe I don't need to write it in this way. I'll just write it in another expression. So as I mentioned that the phase space value, usually you can write it in terms of the exponential form. Okay, so the ratio between these two phase space actually can be expressed as okay. So we can always expand this function nearby the equilibrium value. A star. Then we'll found this ratio to be something that looks like this. Okay. So the reason that we only have quadratic term contribution is because the zeroth order we have basically the same equilibrium value, so they will be subtracted with each other. That's the first thing. So we got nothing. And the leading order basically is something that's related to partial S, partial A. Evaluate A star. By definition, it is equivalent, so this thing is 0. So we don't have the linear order contribution. So the only contribution that's left at the leading order is the second derivative of entropy with respect to this observable A. Okay, so so now you should feel very familiar with the following argument. The first thing is that, as I mentioned several times, this thing is smaller than 0 because entropy is concave. And the second thing is that this object, let me try to write a little bit more steps. This object goes like 1 over n. Okay, and the reason is simple because if we take derivative, entropy is an extensive quantity, so it should be proportional with n, and A is itself a extensive quantity, so it will be proportional with n. So when you take derivative, this factor of n will be gone. But there's another derivative with respect to A, which will give you a factor of n. So that's why the whole derivative, even though the exact formalism of this thing is not clear, but we know the dependence about the system size should pose like 1 over n, okay? And we also know another thing. Basically, this A is a observable, which means that it is a macroscopic quantity, which means that any reasonable measurement in the macroscopic world, the deviation from the equilibrium value will also be of order n large, okay? So this thing will give you n squared, and this coefficient will give you 1 over n. So that means that this thing goes like exponential something that goes like minus n, okay? Because entropy is a concave quantity. Okay, so what does it mean? Again, it tells us that when the phase space at some specific value A, and this A is not equal to the equilibrium value, it will be exponentially small compared with its equilibrium phase space volume. Okay. So what does that mean? It means that let me try to draw that. Maybe I should not say this, but okay, let me try to illustrate the idea. The idea is that, again, this phase space volume is sharply peaked, okay, around the equilibrium value A star. So I'm going to write down something that and explain it backwards. Okay, so let me explain this thing a little bit. So in principle, when I try to evaluate the average value of the observable, I should include all kind of microscopic configuration and average over the whole gamma. And here, this gamma means the whole area below this curve, because I need to integrate over all the possible A value, okay? But now, as we just demonstrated previously, that only the contribution of your phase space that is nearby the equilibrium value plays the dominant role, and it is exponentially dominating. So which means that this average value can be approximated by you just average over phase space that's specified by this specific equilibrium value A star. Okay, so that means that I can just replace this gamma by this gamma A star. And when I do the integration, I can just focus on those microscopic configurations that will give me the value of A star. Okay, but what does that mean? In principle, before you make this approximation, this A of C could have various different value. It could be A star somewhere a little bit away from A star, so you cannot pull it out. But if it is dominated by the weighting nearby the equilibrium value, That means that, oops. That means this object is basically A star. Okay. Once in the integral, it is just a constant A star. Why not just pull it out? So I just take it out. Okay. Once I take it out, you'll see this integration is actually equivalent to the definition of the phase space that is given by the equivalent value of A star, which will just give you 1. So you got this relation. Okay. So that's the whole line of the argument. But the statement that we are going to make is actually to some extent reversed. So what we want is actually we want to calculate this object, right? Because that's the something that we want to predict, but we don't have information at this moment. But if I try to run this statement backwards, what it is telling me is that actually how to evaluate this expectation value, I can simply just do this evaluation. That what I just sum over all the configurations within this phase space gamma with equal weight. And the reason that it is not going to change too much or not going to affect this value of A star is because the dominant contribution is coming from the equivalent value. Even though this integral will include some other values that's different with A star, but the probability of that is extremely small. So I don't care about this very small probability. So I just brute forcefully sum them over as if they are all equal with each other. Okay. So that's why the assumption that microcanonical ensemble is making here is actually a reasonable approach because the weighting that is not at the equilibrium value actually is quite small. Okay. So that's one thing. And the second thing, maybe I should write it down because I just said a lot of things. So the first thing is here's the logic flow. What we want is A star. Okay. Now all, let's say most. Okay. And usually when we talk about microcanonical ensemble, what we meant is given or like fixed E. And observable should be the mean of the observable should be defined by this simply as I mentioned previously, we just consider all the microscopic configuration are equal likely, and then we just take the average over them, and that will give you the equivalent value. And here you can see what ensemble means. ensemble actually meant a rule to calculate the thermodynamic. Okay. So as long as you are able to specify what is the expression of your observable using the microscopic degrees of freedom, and as long as I'm able to specify what are the accessible phase space region, then I'm able to calculate what this observable expectation value is. Okay, so roughly that's the idea. So let's see. Okay, so now I'm going to use a relatively simple example to tell us what do we mean by, like, how to use that idea to calculate explicitly. So consider a simple model. Let's call it is the Ising paramagnets. So Ising just means that it is a two-level system, and this model, Ising model, is used to study magnetic systems in various contexts. So it is kind of important, especially if you work in solid-state physics or magnetism. So the idea is that in a material you have a bunch of atoms, and these little atoms, they carry some kind of magnetic moments. Okay, so let's denote these magnetic moments to be some vector defined on some lattice psi I. Okay, so this vector, to some extent, you can simplify it to be a binary vector. That is, either it points in the z direction of the spin space. Let's use EZ to define the z direction of the spin space. And it has the magnitude mu, which is like the size of the component. And this sigma I is just some value that is +1 or -1. Okay. So it simply is, if we try to model our system using these degrees of freedom, what it actually means is that those magnetic vector are actually some kind of along the z direction or anti-aligned with the z direction, and they are assigned according to this binary variable +1 or -1. Okay. So so that's the degrees of freedom that we are thinking about. So one of the key questions is, what is the energy of the system, or what is the Hamiltonian of the system? So in this simple model about the Ising paramagnets, so if we consider the external field, basically it will coupled with our magnetic moments through this fashion. And this is just simply the Zeeman term that you have learned in electromagnetism, that basically you have apply a magnetic field, and the magnetic moment will try to align with the magnetic field. So you have external field that is applied to all the little magnets in your system, and they are trying to align with each other, align with the field. Okay. So here we are assuming that there's no interaction between these little moments. So that's why it is called the paramagnets. Okay. So if I try to write it further, so now let's assume that this H vector is some vector that's pointing along the z direction of the spins. Then we can simplify this Hamiltonian to be like this. Now this dot product of the z component of the unit vector is just 1, so we got a pure number. Okay, and usually what people consider this summation over all the plus or minus of these binary variables times the unit size of your magnetic moment is basically the magnetization M. Okay, so the phase of paramagnets actually means that these sigma i's, these little magnets are basically randomly oriented. So they are just very chaotic. Somebody is pointing upwards and somebody is pointing downwards. So it's a random variables. Sigma i's are random. Okay, so what does that mean? As we mentioned, that if it is just randomly oriented, we will expect the average value of sigma I to be 0. Okay, so this is almost like the random walk that we learned from the first lecture, that you have equal likely possibility to walk rightward, or you have equal possibility to walk backward, leftward. Okay, so if this thing is average to be 0, sorry, I should have an average. What that means is that the average value of your Hamiltonian, which is the energy, should be 0. Okay, so there should be no problem at this point. So now we can ask, if it is the situation, how to construct the thermodynamic quantities. So from the second law, we can simply write down this this expression. Basically, this is how entropy and energy are related with each other. And because we assume that energy is 0, so we'll have just a simple shift of the terms. We'll get this relation. Okay. So what this relation is telling us is that if we are able to ask what is the expression of entropy as a function of our magnetization M, then we should be able to find the expression for the situation when the system is under the external magnetic field H. Okay. So the question is how to calculate the entropy. Okay. So from the microcanonical ensemble, we know that we are trying to look for the possible phase space. Okay. So we know that the total, let's use n to denote the total number of sites. It should be equal to the total number of spin up sites plus the total number of spin down sites. Okay. So this is something that is by definition. And as we mentioned, M is defined in this way. So so we will find the following relation easily. So M magnetization divided by this unit mu will just give you the summation of sigma I. That is randomly oriented. It could be +1 or -1. So N is basically everybody is +1. So when you add them up together, the -1 and +1 will cancel. So only leave with the +1 that is non-zero, that will be left. But we will double count it, so we will need to divide it by 2. Okay, so that's roughly how this relation is built. And similarly, you can play the same trick, then you know what's spin down. But it doesn't matter. The important thing is that we want to find the entropy. In order to find the entropy, we need to specify what is the accessible phase space. Okay, so the phase space basically correspond to all the possible configurations in your system. So basically, you have Cn sites. You want to choose n spin up and the rest of them to be spin down. So it's just n choose n up configurations. So I'll just write it down. It will just look like this. And if we just insert this n up and n down relation to this expression, you'll see it looks like I should have a bigger parenthesis. Okay. And the entropy should be expressed like this. And at this moment, you probably will notice that this is this n and this m should be a big number, so we can use Stirling's approximation. Okay. And then you will get the function that basically express your entropy using the variable m. Okay, so I'm not going to do that in front of you. Instead, I'll just tell you the key step is that you can use the following equality. Okay, because once you use Stirling's approximation, you will get a bunch of nature log and stuff like that. And once you collect them carefully, you'll see they will have this kind of structure. And once you use this, then you are able to see h over t is basically, you can just input the expression you got. Here's some exercise left for you. Okay. And the physical meaning for that is quite straightforward. Basically, if we try to plot them using the correct parameters, because we know that arctangent h is basically a bounded function between -1 and +1. And what it tells us is that when you apply the external field, we basically gradually align our small magnets to a specific direction. And the comparing energy scale should be the energy that's given by the magnetic field and the thermal fluctuation represented by kBt. So when the energy provided by the external field is much larger than the thermal fluctuation, basically every little spin is forced to align in the same direction. And once they are fully aligned, then the moment will be saturated to the average value, that's 1. Okay. And of course, you can try to change the direction of your external field, then you will be saturated in the -1 value. Okay. So that's a simple example, and you can also try to calculate more if you want to. There are some other derivatives you can do with respect to the entropy. Okay. Good. So let's see. I think there's a misorder of notes, so that's why I'm confused. Okay, so now we notice, or like at least we know what is the meaning of microcanonical ensemble. And the difficulty for microcanonical ensemble is basically you need to specify the volume of your base space under given external under given extensive variables. But usually for general system, this is not provided. We show two very simple examples. One is the ideal gas model, and the other is this Ising paramagnets that we are able to calculate those things explicitly. But in general, it will be a very difficult problem if you only work within the microcanonical ensemble. And also, we also know that the difficulty of microcanonical ensemble came from the fact that energy is fixed. Okay. And from the thermodynamics, we know there's a very important concept that is basically the Lagrange transformation. We can try to change the fixed quantity with its conjugate variable. So in this case, you can exchange it, the fixed energy with the fixed temperature condition. Okay. So in that case, the thermodynamic potential will go from the energy into the Helmholtz free energy. Okay. So the question that it's quite natural to ask is, we start from microcanonical ensemble with fixed E. Is it possible that we can develop some kind of ensemble idea that correspond to this kind of fixed temperature idea? And this ensemble is what people call the canonical ensemble. Okay. Now we are going to introduce the idea starting from the microcanonical ensemble. So the biggest assumption to derive this canonical ensemble formalism is that we need to attach a reservoir. By definition, it's much larger compared with our system. And we only allow the exchange of energy between the reservoir and the system. And the reservoir is defined to have a fixed temperature T. And the rest of the world is basically isolated with our system and reservoir. Okay. So one question is how to evaluate the average value, A star again. So before we construct the canonical ensemble, we can try to consider the reservoir in our system as a whole. Then the whole system has a conserved energy, and we can use our previous expression of the microcanonical ensemble to evaluate the average value of the observable A. It should be E total. Okay, so now we are trying to evaluate the phase average our observable over the accessible phase space. But now the accessible phase space is going to contain two parts. One is the microscopic configuration of our system and the microscopic configuration of our reservoir. But the observable is only defined within the system. So this expression is basically how we evaluate the average value or the equilibrium value of the observable A. So this is the microcanonical picture. Okay. So we can re-express the integral by introducing the delta function. And because delta function tells us that we only want to consider certain condition such that the delta function is, the argument of the delta function is 0. So let me just try to reshuffle things and try to express what this expression means. Okay. So this line should not be difficult to understand. The reason is that we consider the microscopic configurations of our system and our reservoir, but because we are working in an isolated system, so the total energy of the system and the reservoir should be equal to the initial total energy. So that's what this delta function is doing. So basically, you can include all the phase space points, but you require them to satisfy this constraint. Okay. So as we mentioned, if we try to interpret it in this way, then this integral is equivalent to say we are evaluating the phase space which is equal to the total energy subtract the energy of the system. So so why this interpretation is important? Because if we have this interpretation, then we can use our Boltzmann conjecture or Boltzmann's postulate again, that this phase space is actually this expression. Okay. So why this expression is useful? Because as I mentioned before, that the reservoir is kept at the fixed temperature T. And usually what that means is that the reservoir is huge compared to the system size. Okay. So what that means is that this object is a small quantity. So if it is small, what can we do as a physicist? We'll expand it using tidal expansion. I think we should have a course called Usefulness of Tidal Expansion. But anyway, you will see this exponent can be expressed like this. Okay, at least two leading order. And this object is basically 1 over T defined by the temperature of our reservoir. So why it is useful? Because you'll see that the average value of the A star is now related to the microscopic configuration of our system only through this exponential factor, because this is the only place where the microscopic coordinate CS appears. Okay. So there's a name for this thing. It's called the Boltzmann factor. And if we try to interpret this whole object, including this factor and the rest of this exponent, what we are trying to say is that the probability of getting this microscopic configuration psi S, that is this probability of this microscopic configuration psi S, should be proportional with this expression where the microscopic configuration S will give you some specific energy of your system, and you just put it in the exponent with a minus kBT in the front, to the power of -1 in the front. Okay. So in the first homework, we already know if we know some probability that is proportional with something, then it is very natural to ask what is the normalization constant of that. And the normalization constant of that is basically you can sum over these exponential factors. Okay, and this whole formalism to describe your probability is called the canonical ensemble. Okay, so I think I'll stop here, and we will continue about the canonical ensemble. And if you have any questions, please ask me or ask the TA. And if not, have a wonderful weekend. See you next week.